Welcome to this course on digital and discrete control systems. Control systems are essential for modern engineering. They allow us to regulate machines, processes, and devices so they behave in predictable and efficient ways. With the widespread use of computers, microprocessors, and digital devices, most control systems today are implemented digitally rather than through purely analog techniques. This course will give you both the theoretical background and practical understanding needed to analyze, design, and implement digital control systems. The course is divided into two modules. Module 1, Digital Signal Conversion, Z-Transform, State Variables, Stability, and Analysis Methods. Module 2, Controllability, Observability, Digital Controllers, Maximum Principle, Observers, and Microprocessor Control. Module 1, Digital Signal Conversion, Analysis, and Stability. 1.1 Digital Signal Conversion and Processing. The first step in any digital control system is converting signals between the continuous world and the digital domain. Analog to digital conversion, in real-world systems, signals such as temperature, speed, or voltage are analog. An analog to digital converter samples these signals at discrete intervals and represents them as digital numbers. Sampling, the process of taking measurements at fixed time intervals. The sampling rate must be high enough to capture system dynamics accurately without losing information. Quantization, after sampling, values are approximated to the nearest digital level. Quantization introduces small errors, but with high resolution, these errors can be minimized. Digital signal processing, once signals are digitized, we can filter, transform, or analyze them using algorithms. This allows noise reduction, system monitoring, and preparation for control actions. Understanding conversion and processing is crucial because digital controllers only work with discrete time signals. 1.2 The Z-transform. To analyze discrete systems mathematically, we use the Z-transform. The Z-transform is to discrete time systems what the Laplace transform is to continuous time systems. It allows us to represent sequences, difference equations, and system responses in a simpler, algebraic form. Key uses of the Z-transform include representing discrete time signals and systems, solving difference equations, analyzing stability and system response, converting between time domain and frequency domain in discrete form. It provides a powerful framework for working with sampled data systems. 1.3 The state variable technique. Another way to model control systems is with state variables. In this method, we describe the system using a set of first-order equations instead of a single higher-order equation. Each equation represents the evolution of a state variable, which is a quantity describing the system's current condition. The advantages of the state variable approach are: it works well for multi-input, multi-output systems. It provides a direct link between physical variables and the mathematical model. It is convenient for computer-based analysis and digital implementation. It provides a framework for modern control concepts like controllability, observability, and observers. This technique is especially useful in digital systems, where computer algorithms can update state equations step by step. 1.4 Stability of digital control systems. A fundamental requirement of any control system is stability. A stable system is one where outputs remain bounded for bounded inputs. In digital control, stability is analyzed in the discrete domain. The main considerations are: the location of system poles in the Z-plane. If poles lie within the unit circle, the system is stable. The effect of sampling rate on stability. Poor sampling can destabilize an otherwise stable continuous system. Numerical effects, such as rounding and truncation, which may cause instability in practical digital implementations. Ensuring stability is always the first step in digital control system design. 1.5 Time domain analysis. Time domain methods involve studying how a system responds to inputs directly in the time scale. For digital systems, this includes step response, how the system reacts to a sudden input. Impulse response, the system's reaction to a very short, sharp input. Transient behavior, overshoot, settling time, and rise time. Steady-state error, the difference between the desired and actual output as time approaches infinity. Time domain analysis is intuitive and helps us visualize system performance directly. 1.6 Frequency domain analysis. Frequency domain methods analyze systems based on their response to sinusoidal inputs at different frequencies. For digital systems, frequency domain analysis uses tools such as discrete Fourier transforms to study frequency content, Bode plots and Nyquist diagrams adapted for discrete systems, analysis of stability margins and resonance behavior. This approach is especially useful in systems involving filters, oscillations, or periodic disturbances. Module 1 Summary. In this first module, we introduce the foundations of digital and discrete control systems. We cover digital signal conversion and processing, the Z-transform, state variable modeling, stability criteria, and both time and frequency domain analysis. These tools give us the ability to model and analyze digital systems, setting the stage for designing controllers and advanced applications in Module 2.